we have a review problem up here. And it says, suppose we have time going from 0 to 1. And we have a parametric curve, C. And it's parameterized by t cosine 2 pi t sine pi halves t. So, of course, the way that you're reading this is your x of t. This is your y of t. But you're kind of looking at this and like, ugh, that does not look pleasant to work with. And that's kind of a clue, of course. If things don't look nice, it's like, perhaps there's another way. And we're asked to find the integral along the curve of 2xy plus 2x dx plus x squared plus e to the y dy. All right. So we have options 1 plus e, 2 plus e, 3 plus e, 4 plus e, and 5 plus e. Do we have an answer? I've heard a few options people suggested. The answer is A, 1 plus e. Now, B is very tempting. The thing you have to be careful about is this one here. We'll get to where that one is coming from. So, what's going on? Well, we suspect when we see integrals in this format, we're like, I bet you there's a better way. So we try to find a potential function. In other words, what we're really saying here when we try to find a potential function is that we think that it might be the case that this is an integral of the form gradient of f dot t ds or gradient of f dot dr. And if we can find that potential function, we just have to evaluate at the endpoints. So how do you go about finding it? Well, we have information about what might be true. That would be your derivative with respect to x. That would be your derivative with respect to y. So we integrate the derivative with respect to x. We integrate the derivative with respect to y. And that tells us what the function would look like. But then you have to make sure you're consistent. So your overlaps agree. And in this case, you do. So you have x squared y, x squared e to the y. And that's your function. Oh, the lights came on. Okay. And evaluate. Your endpoints, how do you get your endpoints? Plug in your t. Plug in t equals 0, you get 0, 0. Plug in t equals 1, you get 1, 1. So it's start is 0, 0, end is 1, 1. 1 plus e, 0 plus e to the 0 is 1. So there we go. All right. Good. Any questions on this one? Okay. All right. Well, then in that case, our thought for the day, courtesy of Edna Mode. I never look back, darling. It distracts from the now. And probably we'll take it out of context, but you should be focusing on the material from the now. It's kind of a Zen approach to learning, right? Make sure you don't stress about what you did on the first exam or what you did on the second exam. Focus on the third exam. That's where you need to put your energy. That's where you need to put your resources during the next 2.5 weeks. Focus on the now. Make sure you do great on that last exam. Well, not the last exam. You'll have another one. But that's a story for another day. Okay, so I did want to take some time going through and doing a little bit of a longer problem just so we understand what's happening. So it's not that long. I just want to highlight some points. So let C be a curve connecting 0, 0, 0 to 1, 1, 1. Find the following integral. Integral along the curve 2xy plus z cosine x plus y z squared dx plus x squared plus xz squared minus sine of y plus e to the z dy plus sine of x plus 2xyz plus y e to the z plus 3z squared dz. Now, this looks intimidating, but there's a huge clue as to what you're supposed to do with this problem. Beyond the fact that we kind of know what's going to happen, what's a big clue as to what's going to happen with this problem.
It only gives endpoints and doesn't specify a curve.
Right. It didn't say what the curve is. So how is that a big clue? What does that tell us? Well, we can bring our own curve, and it also tells us that it must be that this is not dependent on the curve. Because if it was, they'd have to have given us the curve. Because, we can't have 200 students giving us 200 different answers because they all chose different curves. So it's like, this problem has potential. That's right, I'll be here all semester. Okay. You'll miss me when I'm gone. All right. So I just want to work through finding the potential and make sure we understand what we mean. So that's the goal for this problem. So we think there's potential because there has to be, otherwise this problem is hopeless. So here's our thought process. We have this has to be derivative with respect to x. This has to be the derivative with respect to y. And this has to be the derivative with respect to z. So now what we're going to do is reconstruct our function. So our function is going to be, we integrate the function f sub x dx. So we integrate 2xy plus z cosine x plus yz squared. And, my parentheses game is off. dx. So when we integrate with respect to x, how do we treat y and z? Constants. All right, the integral of 2xy, x squared y, derivative of z cosine x, z sine x, derivative of yz squared, yz squared x. So I'll put that as xyz squared. I don't know. Alphabet pressures, I guess, plus some function which only depends on y and z. All right. Well, that's one way to look at f, but of course we don't know what this function is. But another way to look at f is integrate f sub y with respect to y. So it's like I'm really grabbing this whole thing, even the dy part, and integrating that. So integral x squared plus xz squared minus sine of y plus e to the z dy. All right. Integrating with respect to y, x and z are constants. The integral of x squared y. Integral of xz squared y. So I'll write as xyz squared. Integral of minus sine y plus cosine y. Derivative of e to the z, y e to the z, plus some unknown function, I'll say g, doesn't really matter, x comma z. Okay, and last one, third round, because this is a three-dimensional one, we integrate the last part. So what I really want to build up to is, how do you know if something is a gradient? And there's tests for being conservative, but ultimately I find it's just easier, just go for it. And I want to talk about what happens. Integral of sine x with respect to z. Z sine of x. Integral 2xyz with respect to z. xyz squared. Integral of y e to the z with respect to z. Y e to the z. Integral of 3z squared with respect to z. Z cubed. And something which depends only on x and y. Okay, so at this state we say, now we're going to check for consistency, and then we'll piece it all together. So that's what I just want to spend some time on. How do you check for consistency? Well, you look at anything that says I have multiple variables in the same term. So here is a place where I see both x and y when I integrate with respect to x. So what am I looking for? The same thing when I integrate with respect to y. There has to be consistency. So if I saw an x squared y when I integrate with respect to x, there needs to be an x squared y when I integrate with respect to y. So once I see that consistency, that's one of my terms. All right. What else do we need to check for consistency? Z sine x. So that involves both z and x. So I check, integrate with respect to z. Do we see z sine x? Well, yes. Consistency. So that's going to be another one of our terms. Anything else that we need to check? Yeah, x, y, z squared. Now, where do I have to check for x, y, z squared? All three, because it has all three variables. So I see an x, y, z squared. I see an x, y, z squared. They all have it, so that's all consistent. So that's going to be another term. Anything else? Y e to the z. All right. So I check, and again, I see consistency. That's going to be a term. So that's the check. As long as you're consistent whenever you have terms with multiple variables, you're good. And we've almost finished building our function. What's left for us to add? Yeah, so the cosine y, which didn't have anything except y. Anything else? And the z cubed. And let's see, I'm almost running out of colors. Not quite. Good. Now, is this our potential function? Yes. Now, are there any other potential functions? Yes. How do you get your other potential functions? You add a constant. Not a constant function, a constant. So I could add 5, or I could add 2, or I could feel exotic and add 7. But the point is, that's up to a constant. That's the potential function. So do your integrals and compare. Make sure the overlaps agree, and then put it all together. So to finish the problem, what do we do? Plug in 1, 1, 1. Subtract 0, 0, 0. Plug in 1, 1, 1. You get 1 plus sine of 1 plus 1 plus e plus cosine of 1 plus 1. Subtract, plug in 0, we get 0, 0, 0, 0, 1, 0. All right, we'll get a little bit of cancellation. So we have 2, right, that one plus e. And then sine of 1 plus cosine 1, also known as sine of 1 plus cosine 1. Good. Yeah, can't do anything about that. And you'll notice that wasn't too bad. Yeah, we had to do a little bit of work, but we didn't have to do any like crazy integration. We just had to do some antiderivatives and check. Okay, so that's the process. Now, I keep showing you things that succeed. I just want to point out, what does it mean to fail? So I'm not going to do the whole thing. Here's another problem that says find a potential function if possible, and I work through the integrals of the terms. Are we good? And if not, why not? A lot of things match. So e to the x sine y, that's good. 5yz, that's good. Things with just one variable, you never have to worry about those. So are we good to go? No. What's wrong? Yeah. These parts not matching. So what does that tell you? Not conservative. Now, there is a few cases where you might be able to pull out a trig identity and rewrite, but that's not that case here. So this is not possible. There's no potential function. Now, there are ways you can sort of be sneaky and say, well, I can split it up into two pieces where I have a potential function that works great and then a little piece which is not, but we won't do anything that mean, I think. So anyways, this is how things go bad. That's what we mean when things go bad. All right, well, that brings us to today's topic. You might have noticed that our handout was chosen deliberately a particular color, as we're going to talk about a theorem. It's called Green's theorem. And you're probably wondering, cool, is there going to be a purple theorem and a orange theorem? Nope, just green. All right. But before we get to that, we want to get some context here. So let's remind ourselves about the fundamental theorem of calculus. After all, we can't think about the fundamental theorem of calculus without thinking about fun. So, good. Not the mental. That's not what we think about. We focus on the fun. So the way we usually get exposed to the fundamental theorem of calculus is we say, it's easy to integrate a derivative. So the integral from a to b of f prime of x dx, that's f of b minus f of a. And now if you think about what we learned in the last time, right, our last lecture, we said, hey, there's a special type of line integral which is a very similar flavor. Namely, if we integrate along a curve, gradient of f dot dr, it's f at the end minus f at the start. Which essentially, if you think of what a and b are, a is your start and b is your end. So what's going on? Well, what this is telling us is that you have two ways to do a computation and they're equal to each other. One of the ways is you're doing an integral on the interior, but it involves some kind of derivative. The other way is you're doing an integral, and I know it doesn't feel like an integral, so I'm putting that in quotes. I'll explain what I mean by that. On the boundary. So we say, well, what does it mean to be the boundary of a curve? Well, what does the boundary of a curve feel like? What should it be? If you draw a curve, so imagine you can draw a curve like this. What are the boundary points on the curve? The ends, right? The edges. So our boundary are our ends. So this is our boundary. Now you might say, well, what do you mean by an integral? Well, essentially, when we think about our curve, it's one-dimensional. What's our boundary? If you think about dimension-wise. What dimension is our boundary in? Not dimension as in x, y, z, but just like what type of dimension? Like we are in 3 dimensions. At least that's what we think. The curve is 1 dimension. What are the points are? Where are they living? 0 dimensions. They're 0-dimensional objects. Well, what does it mean to integrate on a point? Well, to integrate on a point means to evaluate. That's what we mean. So essentially, integrating on a point is plugging stuff in. So it says, okay, so integrating on the inside of the derivative is the same as integrating on the boundary the function. Now, one of the consequences we saw is if we integrate something which is a derivative on a closed curve, well, that says that your endpoint equals your start point, so you always get 0. But then I said, well, what if we're not going to integrate a derivative of something? Does this have any meaning? The integral along the curve of f dot dr. Can we do anything with that? So, your first intuition is to say, no, it doesn't fit. Because what do you need? You need to integrate a derivative. And we're just saying it's not a derivative. But what if we don't put it in this column? What if we put it in this column? That's the idea. All right, so that's the motivation. So here we go. Green's theorem. Suppose you have a region in the plane. So here's our region, we'll call it R. And we have a curve which is the boundary of our region. And we're going to use the same symbol that we use for partial derivatives to denote boundaries. So it's this partial symbol. Not a coincidence, that's very deliberate. So there is connection. So whenever you see this, you can read it as boundary. All right, so we have our region, we have our boundary curve. And there's orientation. So when you think back to integrals, these all come with orientation because when you have a curve, you move in a direction. Orientation is built in. Even orientation is built in here. You move from A to B. And what happens if you flip your orientation? If you flip from top to bottom, so you said B to A, what happens to your integral? You flip the sign. So orientation is a plus minus type operation. So there's an orientation here. And so it's going to be very deliberate. So imagine if you can, I brought a small person with me. This is, I don't know if you're familiar with the Smurfs. This is Brainy Smurf. So imagine you were standing on the plane. Then what you want to do is you want to move along the curve in such a way that your region is on your left-hand side. It's like the song. To the left, when you walk the curve, keep the region to your left. Yes? All right. Good. I was debating about whether we should sing it, but I don't know. I didn't write down the lyrics. So, but they're pretty easy to remember. It's to the left, to the left. Good? All right. Good. So make sure you orient your curve so that your region is to your left-hand side. If your curve is oriented so that the region is to your right-hand side, what's going to happen? You have to flip your sign. So orientation going the wrong way will bring a minus sign. All right, now here's the punchline. The integral along the curve of m dx plus n dy, which is this integral we talked about, integral along the curve of f dr. So we're in this column. We're integrating on the boundary of some function f. That should match the integral on the inside. So in this case, the boundary has the inside is r of a derivative. What derivative? Partial n partial x minus partial m partial y. All right. And that's the theorem. A couple of notes. You might notice that we added a little tiny halo to this integral. What does that mean? Well, it's a little tiny circle. If you see an integral with a little circle in it, it means that you're integrating along a closed curve. So your start and stop match up. We already talked about orientation is important. And you might say, okay, I get that. I can talk about orientation on the curve, but how do you talk about orientation on the region? Is there an orientation? It may not be immediately obvious, but the answer is yes. The region has an orientation insofar as we think of it as there's like a top side and there's a bottom side. And so there is an orientation, and this will make more sense later on. Now, on a side note, does this part look familiar? Partial n partial x minus partial m partial y. Have we seen that somewhere before? Ah, it's part of the curl. Whoa, interesting. Which part of the curl? Do you remember? Yeah, like it's that last entry, like in the k direction. So it's the part of the curl that would be perpendicular to the plane. Coincidence? No. No, in fact, this is a special case of a bigger theorem that we're going to get to after Thanksgiving. Okay, so this is, I guess we should make a note here so we remember this. This is part of the curl. All right, so that's the theorem. And yeah, I guess we can start doing a few things. Any questions about the idea here?
Is there any particular reason why you want the region on the left as opposed to the right?
Well, we have to have an orientation. And so the answer is we picked one that's consistent with the results. So essentially, there's always orientation built into calculus. Calculus has orientation from the very beginning, even way back in Calc 1. We just never really talked about it. And so we're going to be talking as we get into higher dimensional settings, we're going to be going up into 3 dimensions, not just in 2 dimensions, but a similar type question. And then we have to talk about, well, you orient a surface versus orient a curve. How do you get consistency? And so it's just a convention that makes sure everything's consistent and so that the theorems work out. So you can just put everything on the right. What happens? Throw a minus sign in, and then it works out. But this is the version for the left. Yes?
So why are we subtracting partial f, partial y from partial x? Where does that part come from?
Because that's what makes it work. Now that's not very satisfying, but I happen to have a sketch of a proof of a special case, which is sort of half of it. Maybe that might help. Okay, but before I throw up the sketch of the proof, were there any other questions? All right. So, why might this be true? So let's do a really simple region. So here, our region, we have a curve that can describe the bottom side and a curve that can describe the top side. And I'm thinking that we go between A and B. So that the boundary of our region is the union of these 2 curves. So if we have this set up, what can we say? Well, it's probably easier to start with this curve downstairs. This curve looks like a function. So there's some function f of x which describes this curve. So that the parameterization is x comma f of x, where x goes from A to B. There's also a function which describes the top curve. Now, unfortunate thing here is that if x goes from A to B, then the parameterization is doing what? It's going the wrong way. So that's why we throw a minus sign here, just to recognize, this is the wrong direction with this parameterization. Okay, so here's the idea. We're going to integrate along the curve just a part of it, m dx. When we do that, we say, well, instead of doing the whole curve, which is our region, we'll do it in 2 parts, curve 1, curve 2. You're allowed to break it up into pieces. And now we say, well, we have parameterizations. So what we can do is we can parameterize. And the nice thing here is that because our x-coordinate looks like x, when we run the parameterization, we really do get dx's. Then we just have to say, well, what happens to these pieces, the m's? Well, everywhere where you see an x, put your x. And then where you see y, you put either f of x or g of x, depending upon which part of the part you are. You have your f of x downstairs, your g of x upstairs. All right. Well, we have 2 integrals. Let's smush them together into 1 integral. Because we're allowed to do that. That's the property of integrals. And now is sort of the great, this looks like you did an evaluation m of xy evaluated from f of x to g of x? Think about going backwards. If I have m of xy and I evaluate at g of x, subtract evaluate at f of x, then I'd get to here. And say, oh, how do I get to this kind of evaluation? Well, I'd integrate with respect to y, the derivative of y. So this is the fundamental theorem of calculus. So Green's theorem is fundamental theorem of calculus. The integral from a to b, integral from f of x to g of x of partial m partial y. But that is just another way to say integral over your region of minus partial m partial y dA. So this shows you how it works if you integrate along your curve of m dx. You end up with this minus partial m partial y. Now you might say, great, where does the other part come from? What would you do? Well, your other special case is you'd think about splitting it up this way, where you have some c and d, then you have a curve and a curve. You run through a similar argument, you'll get partial n partial x. All right. The good news is for us, we have our generic formula. Okay. Let's try this out. Let's see the oriented curve. I forgot the word unoriented curve, but that's okay. We're not English. From 0, 0 to 2, 2 to 0, 2 back to 0, 0. So let's sketch this. So we have 0, 0. We're going to 2, 2. So we're going to mark and add direction. Then we're going to 0, 2. Where is that? Which axis are you on? Well, I'm asking because we need to know. Oh, you meant the y-axis. Oh my, I can't believe I did it again. Oh, sorry about that. Oh, don't worry, the semester's almost done. And finally we go back to 0, 0. Okay, so here is our curve C. It's a triangle. And we're asked to find the integral along our curve of 3x squared y dx plus x plus arctangent y squared dy. Well, what can we do? We could actually do this integral, but we probably wouldn't want to do this integral. Is there any clue about why you wouldn't want to try to do this integral? You probably don't want to try to integrate that. I mean, as much as we love arctangent, that is not looking good. We're a little bit pessimistic here. But that's okay. Because we say, aha, we have a new tool. What can we do? We say, look, this curve, since it's closed, it bounds a region. So we say, okay, so here's our region R. So this is equal to the integral over our region R. And now we just have to remember the formula. So you have your M, you have your N. So we're pulling out Green's theorem. What's the right combination of partial derivatives? Do you remember? N sub x and minus m sub y. When in doubt, just think of the curl. That can help get you there. All right. Well, let's compute these things. What happens when we take the derivative of n with respect to x? You get 1. What happened to that arctangent of y squared? It was a constant when we take the derivative with respect to x. It's gone. It's almost like we planned it to happen. Because we planned it to happen. So oftentimes when you see like something really bad, it's a sign you're not going to have to do it. But you need to know the tool that lets you get rid of it. Okay, what about m sub y? 3x squared. Okay, well, that's fine. We can work with that. So now we have to set up our integral. So the question, do you want to integrate where we slice vertically or horizontally? So vertically, that's your dy dx. Horizontally, that's your dx dy. And you'll get the same answer. So it's not like there's a wrong answer, but there is a preferred answer. Which one's the preferred answer? Horizontal. You might say, why would horizontal be preferred? When you slice horizontally, where do you start from? 0. 0 is our friend. We like 0. So if we can get 0 involved, we do it. So we're going to go dx dy. So we go, where does y go from? 0 to 2. Where does x go from? 0 to y. And then it's 1 minus 3x squared. Well, what's the integral of 1 minus 3x squared with respect to x? It'll be y minus, well, okay, let's not get ahead of ourselves. Integral with respect to x, x minus x cubed, evaluate from 0 to y. Nice thing is we chose to have 0 here. So the zeros cancel. This is really x equals 0 to x equals y. So we have integral 0 to 2 of y minus y cubed. Well, what's the integral of y minus y cubed? Y squared over 2 and 1/4 y to the 4th. Plug in 0 and 2. When you plug in 2, 2 squared divide by 2. 2. 2 to the 4th divide by 4. 4. 2 to the 4th is 16. 16/4 is 4. Our final answer, -2. All right. Any questions? Okay. Well, in that case, your turn to try a problem. This is from an exam. Not the exam you're going to take, but this is from an exam 3 from a few years ago. And I copied it as the problem is stated. Find the integral along the curve of 3y minus arctangent x to the 6th. I know, they just love throwing in arctangent. It's their great distractor. Plus 7x minus cosine square root y minus 1 dy. C is the circle x squared plus y squared equals 1, traversed counterclockwise. Well, you've had a few minutes to think about this one. Do we have an answer? 4 pi? Anybody else get 4 pi? Good, because that is the answer. Because what do you do? N sub x minus m sub y. 7 minus 3 is 4. You're integrating 4. The 4 can come out. You're integrating 1. What do you find when you integrate 1 over an area? Area. Yes. So if you integrate 1 over a region, a two-dimensional region, you're finding the area. It's like, well, what's our region? Circle radius 1. How much area is in a circle radius 1? Pi. So 4 pi. And there you go.
So what is this, like what is 4 pi? Like what is that value?
Oh, that's a great question, which we won't get to today, but we will get to next time. I do want to say, we have a few minutes. It's enough time to say an application. Yes?
Would this have got full points on the exam?
Yes, this was basically the solution. Yeah. So yes, this would have gotten full points on the exam. And in case you're wondering, look at the handout. Every single exam 3 has always included a Green's theorem problem. They love Green's theorem. Almost more than any other topic, it's like there's going to be a Green's theorem type question. So make sure you know it. This one was a little bit of an easier one when it comes to green theorem. Okay, so applications. People are always like, what is this good for? Can you do anything with this math stuff? So there is something called the planimeter. This is a real thing. You don't really use it much nowadays because of computers, but it used to be there was a time when there were not computers. And so in those dark ages, you wanted to still do stuff. So there was a device that was created that says, suppose you want to find the area of a shape. But your shape is very bizarre. Lots of squiggly lines. Like it might come from nature. You know, like how do you find the surface area of a lake? So there's a device, and it roughly looked like this. There was a mechanics here, and then there was an arm attached to a point. And you would grab the point and you trace your region, and then once you got back to where you started, there was a readout on the machine, and the readout was the area of what you had just traced. So how do you go from tracing an object to finding the area? What they realized is when we trace the object, we can think of doing a line integral. So they created a mechanical device that was computing a line integral. Essentially, it was computing this integral, because the machine understood where you were at and where you were moving. So it was computing this integral. But what is this integral? If you apply Green's theorem, it's an area. So you could convert going on the outside edge to figure out the area. And we have a minute. Do you want to see an application, or do you just want to trust me in? I'll write up the application. This is essentially how do you find the area of an ellipse, and but it's not too bad. But it looks like we'll stop here.